So first of all, we start our presentation with the basic and principle of ICE. What is ICE? ICE is a heat engine in that convert energy from the heat of burning gasoline into the mechanical work or tool. ICE provides high durability and drivability. It commonly used in a car with a gasoline, diesel, and alternative fuel like a propane, biodiesel, and natural gas. Next, ICE can combine with a hybrid electric for increased fuel efficiency. So, combustion and ignition occur inside the engine, converting energy to work. Engine consists of fixed cylinder and mover piston. Lastly, combustion gas push the piston up, rotate the crankshaft, and drive the vehicle through a gear system.
In the figure given, a diagram of an engine dynamic is shown. The main parts consist of the main physical important submodels, such as engine control unit and the in-cylinder process. There are two dynamic subsystems that make up the intake manifold block, while the fuel dynamic model depicts the effect of fuel wall wetting and evaporation in order to estimate the real port air-fuel ratio, which substantially influence engine torque and emissions. The air dynamic model computes the airflow rate through the throttle body and the engine port. The in-cylinder process for torque and pre-catalyst emission estimation has been characterized using black box neural network models. Based on the synthesis of steady-state experimental data, due to the requirement to limit the computing time with adequate precision, an engine control unit module, which is an ECU, has been developed in order to stimulate the effects of different control strategies. The main objective here is concerning about air-fuel ratio control in order to guarantee optimum catalyzed performance, especially in control transients because of the different dynamics of air and fuel flow. According to this goal, the ECU module library offers a selection of several engine control strategies, which are mainly composed of a closed-loop lambda control and a model-based fuel film compensation.
Science, please!
Do the words auto mechanics make you curious? Actually, it's a cinch. A car is made up of wheels, seats, fuzzy dice, a body, and an engine. The internal combustion engine. The engine works in 4 stages. First, a valve opens and the piston lowers, letting a mixture of fuel and air into the combustion chamber. Second, as it comes up, the piston compresses the fuel-air mixture. Third, a spark from the spark plug ignites the mixture, which pushes the piston down again. Fourth, the exhaust valve opens and as it comes up, the piston pushes the spent gases out. And the cycle starts over again. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust.
Assalamualaikum and a very good day to all of you. So today I would like to talk about method of performance analysis. So it got 6 points, and the first point is thermal efficiency analysis. So it is crucial for fuel conversion efficiency, and it is calculated under various operating conditions. It also understands overall energy conversion efficiency. The next point is emission analysis. So what is emission analysis? It measures pollutants from combustion, it minimizes NOx, HC, CO emission, and it also aims to meet regulatory standards and reduce environmental impact. So the third point is combustion process analysis. So it understanding combustion process essential, the homogeneous charge compression ignition combustion use, and it also can help to improve thermal efficiency and reduce emission. The next one is scavenging system design analysis. So what is scavenging system design analysis? The two-stroke cycle engine scavenging system design for crucial performance. It utilizes CFD simulation like K-3V for efficiency and emission optimization. So for the 5th point is experimental studies. So what is experimental studies? Experimental studies is validate theoretical models and simulation. It also tests engine system under controlled conditions, and it measures performance parameters like combustion, pressure, temperature, and efficiency. And the last point is linear alternator integration analysis. So what it is, it analyzes impact on system efficiency based on brushless DC motor technology. It also has high efficiency and power density.
Hello, my name is Azizul and I will continue with performance calculation. So, based on the graph and the data given, we know T1 is 24 Celsius and convert to Kelvin, which is 297 Kelvin, and P1 from the graph is 4.5 kPa, and we can get the value of VR1, U1 and U1. For step 2, from the graph, P2 is equal to 9.4 kPa, and we can get the value of T2, VR2 and U2. For step 3, also referring to the graph, we know that the pressure is 9.9 kPa, and we can get T3, VR3 and U3. And for the last step, step 4, from the graph, the pressure is 5.2 kPa, and we can get T4, VR4 and U4. We must calculate Qin first, which is Qin U3 minus U2, and we get 14.651 kJ per kg. For Q out, we get 5.028 kJ per kg, and for W net, which is equal to Q in minus Q out, which is 9.623 kJ per kg. So for the thermal efficiency, is equal to W net divided by Q in. It is equal for 0.658 and convert to percent, equal to 65.68%. And for the MEP, which is mean effective pressure, which is W net divided by V1 minus V2, so we get 2.75 kilopascal.
From the journal of advanced internal combustion, there are some suggestions to improve the system. First of all, by ultra high pressure injection. So, higher pressure injection can improve engine performance and reduce emission by increasing power output from 100 megapascal until 160 to 180 megapascal, and even over until 200 megapascal. This decrease fuel consumption and increase engine efficiency, improving the brake thermal efficiency and fuel consumption. It also facilitates quicker heat release, shorter combustion pace, and faster fuel automation. The second suggestion is by double compression expansion engine. Advanced in engine theory, the 4-stroke engine configuration stay the same. It introduced the concept of a split cycle engine, which run on open cycle and has to spread piston cylinder for the compression and expansion stroke. Comparing this approach to standard engine, it has the most potential to enhance thermal efficiency. Next, we can improve our system by variable compression ratio. So a variable compression ratio engine aims to reduce emission, enhance thermal efficiency, and enhance engine performance by adjusting the compression ratio to allow for faster flame speed, shorter ignition delay, and improve brake thermal efficiency. Then reducing fuel consumption and CO2 emission. When consumption improve brake thermal efficiency and produce combustion characteristic, the pit cylinder pressure rise. The last, by engine knob control. This concept can affect thermal efficiency and engine performance, especially when traditional spark ignition is used in high load region. There are several methods to detect knob, which is direct measurement of in-cylinder parameter, indirect measurement, heat transfer analysis, and temperature analysis. This method efficiently repress knob, and rapid flame propagation can reduce and gas auto-ignition and provide precise auto-ignition timing, which can provide focus heat release.